Eh ben, merci beaucoup. C'est toujours un plaisir pour moi de venir à Grenoble. Je ne vais pas me vanter de mon implication dans les annales de l'Institut Fourier parce que mon temps de réaction n'est pas toujours optimal. Alors, je vais commencer par poser English. I will start by asking a ridiculous question. Suppose that X is a Riemann surface. And let's say it's of genus G, and I want it compact, no holes. So here's a nice picture. This is the only picture in this talk. I apologize for that. So the stupid question is, how can I classify or construct all vector bundles on this Riemann surface? So question, classify or construct all vector bundles on X, and here I mean up to isomorphism. Okay, so anybody who's worked on Riemann surfaces will know this to be a very naive question. So there are two invariants that we can use to reduce a little bit the problem, partition the problem. If you want, there are discrete invariants of vector bundles on a Riemann surface. First one is the rank. Everybody knows what the rank of a vector bundle is. And then there's another invariant, which is the degree of a vector bundle. So this is a positive integer. The degree of a vector bundle is an integer which could be positive or negative. And just very naive, just very quickly, there are two ways to define the degree. One of them, if you know about Chern classes. So degree of V is the first Chern class of V. This belongs to H2 of the curve, which is isomorphic to Z. So this is one way of defining the degree of your vector bundle. Another way of defining the degree is you take a section, which is a rational section. So this is also equal to a number of zeros. Oops, maybe poles. Wait. Zeros minus number of poles of a non-degenerate rational section. Okay, so I can ask how to classify, construct all vector bundles on X of fixed rank and degree, of rank R and degree D. Okay, let's look at one case where this is very well known. If I look at rank 1 bundles, so line bundles, so example, R equals 1 and D is anything. Then I'm looking at so-called pick. Pick D is the set of all line bundles on X of degree D. And this is known to have the structure of an algebraic variety, projective variety, which is the so-called Jacobian of X. It is isomorphic to a quotient like this, and lambda X is isomorphic to Z power 2G. And there are many ways of actually constructing this Jacobian. If you know enough about your Riemann surface, you can construct this Jacobian, and you have a nice answer, the best answer you can hope for such a silly question. A nice algebraic variety parameterizing all line bundles. Okay, so we can further decompose a little bit this question in the following way. Suppose I have a vector bundle. Then I can maybe write it as a direct sum of lower rank vector bundles. And then I can, again, split each of these lower rank vector bundles into direct sum, maybe, of even lower rank vector bundles. And I can do that until I have indecomposable vector bundles. So I can break down my vector bundle into a direct sum until I cannot do anymore. So here's a nice fact, which probably goes back further, but at least you can find a nice account of it in a paper of Atiyah. It says any vector bundle V decomposes as a direct sum of indecomposables, where ij indecomposable. Vector bundle and mi, mj are just the multiplicities. So stated like this is complete triviality. You don't need Atiyah. I just gave you the proof. The important fact is that this decomposition is not at all canonical, but the vector bundles that arise are uniquely determined, and the multiply is also uniquely determined. OK, so let me rephrase this a little bit. Classify, construct, all indecomposable. Vector bundles of x on x of rank r and degree d. OK, I only did things completely trivial. This is still a completely impossible problem. But let's just look at some examples. Let us just look at the first example. Genus is equal to 0. So x is the Riemann sphere. In this case, we can do everything thanks to a theorem of Birkhoff, although I'm sure it was known way before. So first of all, for any integer n, there is one nice line bundle up to isomorphism, which is this serre bundle, O of n. This is the serre. At least we call it serre line bundle. Maybe somewhere else they call it differently. You can describe it as the set of rational functions with which are allowed to have a pole at, say, 0 of order up to n. This is one nice line bundle, and the theorem of Birkhoff says the following. First of all, peak n is restricted to just this one point. There's only one line bundle of degree n. OK, and then, even nicer, all indecomposable vector bundles are of rank 1. So the obvious corollary is that any V decomposes the direct sum of line bundles. And this decomposition, as I said, is not canonical in any way, but multiplicities are completely determined by V. OK, so this is full answer when x is of genus 0. And this is already quite useful. Now let's look at the next case. G is equal to 1. So x is an elliptic curve. And in that case, what is well known is that the Jacobian of x is isomorphic to x. So I mean, I wasn't very precise. Maybe for this isomorphism to be canonical, you have to choose a point in x, some origin. But in any case, you have a as good as possible description of the Jacobian. But here's the really amazing theorem due to Atiyah, I think 57. It says the following: for any pair R and D, there exists a almost canonical, let me just say canonical, although it's almost canonical, bijection between the set of indecomposables, vector bundles of rank R and degree D, and X itself again. So not only all line bundles of fixed degree are in bijection with the points of the curve, but actually rank 17 and degree 943 vector bundles are also a canonical bijection with points of x. And so here is one way to do that. Just show you, let's look at 2, 1. Rank 2 vector bundles of degree 1. How do we construct them? Well, we take a line bundle of degree 1. And then the claim is that there exists a unique non-split extension between the trivial vector bundle of rank 1, let's call this V, and this line bundle of degree 1. And so the assignment that takes L and gives you this rank 2 degree 1 vector bundle is the bijection. So in other words, you construct all the rank 2 degree 1 bundles by considering unique non-split extension with a fixed rank 1 and degree 0 line bundle. And you iterate this process. And if you do this in a smart way, then you can see there's an SL2Z somewhere. And what you're really doing, although in 1957 none of this business was around, is you're considering a braid group action on the derived category of coherent sheaves on your elliptic curve, which is generated, and this is why I'm telling this, by some Fourier-Mukai transform associated to a spherical element, spherical object, which would be O of x, something like this. So 30 years ahead of his time, Atiyah was able to use all this machinery to produce this very nice result. OK. What can we do in higher genus? Well, I can erase that. I have to erase something. So. What can we do in higher genus? Well, nothing as good as that, definitely. Because as we all know, there's a world. Everything goes south when you move from genus 0 or 1 to higher genus. And so certainly, there is no hope of getting any classification of vector bundles on higher genus Riemann surfaces. So I think Turing was able to do something in genus 2 and rank 2. But certainly, it's really hopeless. Let me just say G greater than 1. Hopeless to get as nice results. Hopeless. OK, so as usual, we ask better questions. Or better constructions. So the first thing that people do is, OK, we cannot describe them all. Maybe we can still show that the collection of all vector bundles has a nice structure, something like an algebraic variety. So we can construct something which we call moduli space of all vector bundles of rank R and degree D. And this is not going to be such a, well, it is very nice, but it's not an algebraic variety. This is what's called a moduli stack. And it's not separated. Still, you can do lots of things with it, but not at all like the Picard variety. Other thing you can do is you can insist that you really want an algebraic variety. And so then you're going to construct a moduli space. Let's say a nice moduli space of nice vector bundles, which in this case are semistables or stable vector bundles of rank R and degree D. And so, for instance, suppose R and D are relatively prime, then you can do that. And you will get, after some work, a nice, smooth projective variety that you can study. So this is what people have been doing for a long time. But I insist on doing something else that's a bit strange. So what I want to talk about is let's try to count. We cannot classify them. We cannot construct them. Maybe we can still count them. So count indecomposable vector bundles. So this is very easy. The answer is infinitely many, as soon as we're in genus greater or equal to 1. So in order to make this more fun, we should now move to the setting where x is a smooth projective curve defined over fq. So now we have a finite field, smooth projective curve defined over a finite field. And here's a nice fact that you can prove using some standard reduction theory for vector bundles on curves. For any fq, for any x over fq, smooth projective curve, for any r and d, the number of indecomposable vector bundles on x of rank r and degree d is finite. So the number of indecomposable vector bundles, if you are in over a finite field, this is a finite number. In other words, if you go too far into this, so these this is an algebraic variety, so it has finitely many points over a finite field. But here you have lots of other vector bundles which might be indecomposable, even though they are not semi-stable. And you have to make sure that you can stay at the, you don't have to go too deeply into this stack. Otherwise, you cannot be indecomposable. OK, and so this number, or a small modification of this, I want to consider geometrically indecomposable vector bundles, meaning they remain indecomposable when I pass to the algebraic closure. So this number, let me just call this AXRD. Depends on the curve, depends on R and D, a priori. OK. Let's do some examples. What can we say about these numbers? So we know they exist. That's one thing. Then we can easily compute them for x of small genus. So g is equal to 0. So AP1 RD. This is 1 if r is equal to 1, and 0 if r is greater than 1. OK, suppose now g is equal to 1. So x is an elliptic curve. AXRD is nicer because it's always the number of points of the elliptic curve over the finite field for any r and d. So this theorem of Atiyah is so beautiful. It works over any finite field and many other fields as well. OK. So as you see, this number depends on the curve, which is a good thing. But somehow here we see it just depends on the number of fq points of the curve. So this is going to be the case in general. And so in order to make this statement more precise, I want to introduce the zeta function of the curve, which is a gadget to compute all the number of points of x over all extensions of fq. So let me define this zeta function, or recall the definition quickly. So the easiest way to define the zeta function is to just view it as a generating function for the number of points over all extensions of fq for my variety, here my curve. So zeta function is defined like this. It's the exponential of the sum for all n are equal to 1 of x of fq to the n, z power n over n. You can define this for any smooth projective variety, for any variety if you want. And the beautiful theorem due to Weil is that there exists a nice polynomial with integer coefficients that describes this generating series. This is of degree 2g such that zeta function is equal to Lx of u, and then I have the ratio by 1 minus u, 1 minus q u. So beautiful thing is that this a priori encodes infinitely many numbers, number of solutions of this equations defining x over all extensions of fq. Turns out everything is a rational function, which means that if you just know the 2g plus 1 values, you can determine all the other ones. U is z. Thank you. Thank you. OK, and then this number here, the roots of this number, of this polynomial, are what's called the Weil numbers of the curve. They have a nice cohomological interpretation that I won't give. But you can factor this polynomial, obviously, and the roots are called the Weil numbers. Inverse roots, maybe. So sigma I are the so-called Weil numbers of x, and they satisfy some important properties. Namely, they are all of absolute value q power 1/2, and they come in complex conjugate pairs. So sigma 2i minus 1, you can reorder them such that sigma 2i minus 1 times sigma 2i is equal to q. OK, and then, for instance, let me just give some example that you can get directly from here. The number of points of x over fq is equal to 1 minus the sum of the sigma I plus q. This is the number of points of your curve or of fq. And you can also prove, but of course it does not follow directly from this formula, but you can also prove that the number of points of the Jacobian of x over fq is the product 1 minus sigma I. And this is an integer. OK, so let me state the theorem. Like I said, the main theorem. Main theorem says that there's an explicit formula for the number of indecomposable vector bundles, this A xrd. And this formula is a polynomial in these Weil numbers. Just like the number of points over fq is a polynomial in the Weil numbers, or the number of points on the Jacobian is a polynomial in the Weil numbers. There exists such a polynomial in any rank and degree. So here's the theorem. Yes. Actually, for some of this was proven by Anton Melit. So there exists a unique polynomial, AGR. It has some nice integrality and positivity properties. It is invariant under a certain group. The group is the group of symmetries. So there is no way to reorder canonically the sigma i's. I can always, they come into pairs, and I can permute the pairs between themselves. This gives me a certain group, which is SG cross S2 power G, that acts on these Weil numbers. And these Weil numbers satisfy some property that I just wrote. So there exists a nice symmetric polynomial, positive coefficients, integral, such that for any finite field fq, for any curve of genus G defined over fq, and for any degree, this number axrd is just the evaluation of this polynomial at the Weyl numbers of my curve. So there's some universal formula telling you how many indecomposable vector bundles you will find. No way to classify them, no way to construct them. At least over a finite field, you can always count them. So here's one example. R equals 2, and G is equal to 2. So then you get the Jacobian. The Jacobian always acts, tensoring by line bundle of degree 0. And then after you multiply by the Jacobian, you have a q plus 1, q squared minus sum of zi. But then you have a plus 2, not a plus 1. There's a plus 2. OK. There's a big formula. I don't know if I should really try to write it down. But one thing that I want to say is that it is not obvious at all that it is independent on the degree. So there's no canonical way, starting from an indecomposable vector bundle of rank r in degree 0 to get an indecomposable vector bundle of rank r in degree 1. In particular, the moduli spaces that describe vector bundles of rank 0, of rank r degree 0 or rank r degree 1 are quite different. They look different, and they are different, but somehow they have the same number of points. So I'm not going to write the formula. But let me just say that it's horrible the first time you look at it, and then you fall in love with it after seeing it 50, 100 times. And this formula was conjectured by Hausel and Rodriguez Villegas in a different setting that I will come to right now. But let's just say that the formula is something like this. You take a sum over all partitions, and you have a product for all boxes in your partition of a big ratio that is itself a product for all I goes from 1 to 2g of some terms which look like McDonald statistics. McDonald polynomials statistics. And actually, this is a ratio. So this is what this formula involves as a main ingredient. Is a big sum indexed by all partitions, big product of all boxes of the partition of some complicated statistics. You have it involves, if I draw a Young diagram, I have a box here, then I have to consider how many boxes above it. This is the leg. And then the arm is how many boxes to the right. Anyway, OK. So if you are used to passing from characteristic 0 to to positive characteristic, then the natural question is, OK, you have counted something in characteristic P because it was finite, and you could use whatever trick to do it. What does it mean for the characteristic 0 problem? Right? Usually you have in very favorable cases, you have an algebraic variety. You can either, it's defined over Z or some ring. You can reduce it to finite fields. You can count the number of points. Or you can look at the C points of your variety, and you can take the cohomology. And maybe these two give the same numbers. So this doesn't work here. But something quite close does. So we do not get the same thing as the Betti numbers of the moduli space of indecomposable vector bundles, because the moduli space of indecomposable vector bundles is ugly. It's just constructible. It's not a moduli space. It's a moduli stack. It's singular. So you don't expect anything nice with indecomposable vector bundles. But it turns out that there is a nice and important algebraic variety associated to the curve, which whose Poincaré polynomial is given by this counting. And this is the moduli space of Higgs bundles. So let me say Higgs bundle on X is a pair V phi. So V is a vector bundle. And phi is a map from V to V tensor, the canonical bundle. You can view this as kind of taking the cotangent bundle. So the moduli space of Higgs bundles looks like a partial compactification of the moduli space of vector bundles, if you put semi-stable in the right places. But this is an important algebraic variety. So let me write Higgs stable. So let's fix R and D, and let's assume for simplicity that they are relatively prime. So Higgs stable of rank R and degree D is the moduli space of all pairs V phi, such that V is of rank R and degree D, and the pair V phi is stable, which is something that I don't want to spend too much time on. Let's say it's just a condition that makes this set be parameterized by a nice algebraic variety. And this is a smooth, quasi-projective, symplectic variety. And it has lots of important properties. There's a map to affine space, which is a Hitchin fibration, which makes this into an integrable system. And it appears in many places in mathematical physics and lots of other places. This turns out to be diffeomorphic, just diffeomorphic, to the variety of maps from the fundamental group of X minus a point to GLR C, such that the monodromy, say gamma of the puncture is e power 2I pi d over R times the identity up to conjugation by GLR, which is this so-called character variety of genus G and rank R. And so the result is that the Poincaré polynomial of this thing is given by this crazy formula. This was the conjecture of Hausel, Rodriguez, Villegas. So they were not interested in counting indecomposable vector bundles. This weird question from algebraic geometry point of view. They were interested in these two varieties. So here's the theorem. The Poincaré polynomial of this moduli space of stable Higgs bundles is equal to, up to a power, up to a rescaling, specialization of this polynomial counting indecomposable vector bundles. So in some sense, counting indecomposable vector bundles turns out to be the same thing as counting stable Higgs bundles. And the reason is a bit strange. So maybe just a vague, very vague idea. If I take a Higgs bundle, I can always forget the Higgs field, and I land into vector bundles. So naively, I could say, well, maybe stable Higgs bundle means that the underlying vector bundle is indecomposable. So this is not true, but somehow it becomes true if I deform this. So I can deform this picture in such a way that generically an element here, so over the family, the fiber, so this thing will be fibered exactly over the indecomposable vector bundles. So you want to deform this picture. So that's, let's call this map pi. Pi is a fibration over indecomposable vector bundles. Okay. How much time have I left? 5. Okay. I thought I went really fast and rushed everything. Okay. So I was supposed to talk about Lie theory. So for the moment, it seems to be just combinatorics and algebraic geometry, no Lie theory whatsoever. So 5 minutes of Lie theory. And most of it is conjectural. And everything is based on an analogy. So if you don't like curves, then maybe you can try to discretize them and look at some combinatorial analog of curves, which are called quivers. And people have been doing that for a very long time. Lie theory. So fruitful analogy. Vector bundles on curves look a lot like representations of graphs. And in this setting, a graph is called a quiver because it's much more poetic, I guess. So what is a representation of a graph? So here's a graph. Right, I have three vertices here and 1, 2, 3, 4 arrows. So a representation of this graph over some field K representation of a graph. And let's call this graph Q has vertex set I and edge set E. So I have to give you a collection of vector spaces. So K vector spaces, Vi, one for each vertex. So just picture a vector space sitting on top of each of these vertices. K finite dimensional vector space. And then for every arrow, just a linear map. And that's it. So XH from V source of H to V target of H for any arrow H, E. But of course, there's a notion of isomorphism. So two representations are isomorphic if you can change basis in the various vector spaces and get one from the other by conjugation. So there's a well-defined notion of indecomposable representation of a quiver. And it's an abelian category of dimension 1, meaning that the moduli stacks are smooth and so on, just like quivers. So you can either think that you replace your curve by just discrete number of points, and somehow you relate the different points by a line to remember that it's a curve. But this is kind of just more fantasy than anything else. Or you just say both categories are of global dimension 1, satisfy the same homological properties. That's more. OK, so here's the theorem of. So I'm going to put a bunch of people here. Katz, Hausel. No time for the others. So for any Q, for any dimension, for any collection of dimensions, there exists a polynomial, AQD. This is the theorem of Katz. The fact that it is positive coefficient is due to Hausel and some of his collaborators. I really should write the names. I feel bad. So Letellier and Rodriguez-Villegas. And there are some others that I'm part of the others, so it's OK. So there is a polynomial counting indecomposable. Representation of Q over FQ. Meaning now it's a polynomial in one variable, and there are no moduli spaces of quivers. The only thing you can vary is the size of the finite field. Okay, and number 2, let GQ be the Borchertz and Kac-Moody Lie algebra, finally, whose Dynkin diagram is Q, is the graph underlying Q. So for any graph, I can associate a infinite dimensional, usually Lie algebra. If the graph turns out to be one of these ADE types that you have seen in many textbooks, then this is a simple finite dimensional Lie algebra. But you can do for any graph. There's a theory of Borchertz, Kac-Moody Lie algebras associated to any graph. And it gives you a nice Lie algebra. And it has weight spaces. And you can talk about the character of such a Lie algebra. And so then AQ, so the sum, the generating series of these numbers, AQD, sum over D, of 0, the constant term, e power d, is equal to the character of the positive half of this Kac-Moody-Borchertz Lie algebra. So somehow this number, this polynomial counting indecomposable representations, if I look at just the constant term, which is a bit strange, it's a counting polynomial, the leading term, I want to throw it out and just keep my eyes on the constant term, then this gives me exactly the weight multiplicities, the root multiplicities, for this complicated Lie algebra associated to the graph. And then just 2 more things. One is a remark. Molik and Okunkov defined an extension, a z-graded. So they define geometrically using quiver varieties, Nakajima quiver varieties, and the quantum cohomology of these, define a z-graded extension. Let's call it G tilde Q of GQ, and conjectured is that now I take the sum, and now I don't take just a constant term, I take everything. Then this is the graded character of this Molik-Okunkov Lie algebra. So somehow there is a beautiful Lie algebra out there who accounts precisely for the number of indecomposable representations of the quiver. And finally, here's the conjecture. I'm going to finish with that. So, I mean, the way I'm going to state it looks not very, how to say, it's not really a conjecture because there's the word natural in the middle, so it all depends what you think is natural. But so let's say the idea instead of conjecture is that there exists a natural Lie algebra of genus G. So this is G for the Lie algebra. This is G for the genus. Sorry. And it should have a weight decomposition according to the rank and the degree. And again, for any RD, GRD, the dimension of this Lie algebra, should be the constant term of this polynomial. And this is given by some interesting formulas. These constant term of these polynomials, interesting formulas. And second of all, there exists an extension of this. So extension G tilde G of GG. Now it should be graded. But before, Katz's polynomials, the name of these polynomials, are graded by just one variable, t. Here I have a bunch of variables. The right framework is to say this is a Lie algebra in the category of GSP2G C representations. So the underlying vector spaces is a GSP2G representation, such that for any R and D, the character of G tilde RD is now precisely equal to AGR. So this lives in a ring which turns out to be exactly the character ring of this GSP2G. And I should definitely stop here. Just want to end by just one observation, which is really funny, is that AG, so let me look at the quiver with one vertex and G loops. So this is and look at the Katz's polynomial. This is a one vertex, G loops, and I look at the dimension vector R, and I look at the value at 1, then this turns out to be equal to AGR at 0, 0, 0, 0. So this is, through this counting, there's a strange coincidence between counting indecomposable vector bundles for this quiver, which looks kind of like the real part of a genus G curve, like a bouquet of lines, circles, evaluated at 1, and evaluating this counting at 0 for the genus G curve. And I have killed my time over and over, so thank you very much.